So, hello everyone, welcome back to my lecture. And now in this section, I'm gonna tell you something about my program AICON. So, yeah, if you still remember that in the last section we talked about the calculation of electronic relaxing time. So, the main difficulty of calculating the electronic transport properties is how to calculate this electronic relaxing time. If you need to calculate using first principle method, it will cost a lot of time. So some approximation should be introduced, and yeah, the total electronic relaxing time according to the Mason's rule should be include the scattering effect from from the acoustic phono branch, optic phono branch, impurity, gray boundaries, etc., etc. In my program, I only consider the first three scattering process. Let's see. First, the acoustic phono scattering. This scattering process perhaps is the most important scattering process in the intrinsic temperature and Carrier concentration range, which can be described by the deformation potential theory proposed by Badin in 1950s. The main assumption behind this series are the studied objects are isotropic crystal. All the scattering process are elastic. The materials are under non-degenerate state, which means pure or very low doping. The energy band is parabolic, and the effective mass of carrier equals to the mass of electrons, which also means constant energy surface is sphere. Badin's theory was proposed for calculating the mobility of nonpolar semiconductor, such as silicon. So this theory have to be extended in order to be applied to a wide range of materials. For example, usually the materials is under degenerate state because of the doping. The energy band is not strictly parabolic, especially near the boundary of breaking zone. Also, the constant energy surface are usually not sphere. Ellipsoid constant energy surface should be more common. At the first step, we need a model to describe the band energy wave vector relationship, which usually use Klein band model. In this model, for lowest conduction band or highest valence band, the energy dispersion law can be expressed as this. Here, vertical and parallel symbol represent the longitudinal and transverse direction of the ellipsoid constant energy surface. Epsilon is band energy, epsilon g is band gap. The energy dependence of the the parts in the brace indicating the band non-parabolicity. So after we have the formula to describe the band energy, we can write down the energy dependence of effective mass and also the density of state. Here, MD is so-called density of state effective mass, with N represents the band degeneracy due to the symmetry. So based on this Kanban model, the deformation potential theory can be expanded, and the scattering rate for the electron acoustic phono is like this. Here, E1 is a deformation potential constant. CL is a direction average elastic constant. The part outside the bracket is the same as the formula proposed by Badin. The part in the bracket is a function of Z and beta, describes the energy dependence of the squared coupling matrix element. Its correction to the parabolic band model. Well, in polar crystal, at some temperature, the polar scattering from long wavelength longitudinal optic phonon should also have the same temperature dependence as the acoustic phonon. It has a form as this. Again, the part in the brass represent the energy dependence of the squared coupling matrix elements and the screen effect from the free carriers. Also, in real applications, there are always doping in semiconductors, so we also include the scattering from ionized impurities. So based on the models I introduced above, all the transport properties, I mean, especially the electron relaxation time can be calculated, and all the key parameters we need to know are just these 6 parameters, and they all can be calculated by DFT now. So for the light thermal conductivity, we used the bi-Kelvin model. The original Kelvin model based on these 4 assumptions and only consider longitudinal acoustic phonon. Later, this theory was developed, and Morelli gave specific formulas for 3 acoustic phonon branch. Each of them include 2 parts, and each part can be calculated as this. Many parameters here are just constant or can be easily obtained. There are only 3 parameters need to be carefully calculated. They are Grayson parameter gamma, phonon velocity v, and the by temperature for each acoustic phonon branch theta. Before these parameters need to be obtained from experimental or fitted from experimental data. Now they can be calculated using DFT directly. So furthermore, I improve the model by adding the contribution from optic phonon branch because they are important at high temperature or for a compound with complex structures. The updated formula I show here. Using a weighted average method, I compressed all optic phonon into one studio optic phonon branch, and in its kappa formula, I use Einstein model instead of the Debye model to calculate its specific heat, which should be more accurate for optic phonons. So until now, I have talked about the model for calculating electronic transport properties and the phonon transport properties respectively. So how good are these models? Well, electronic transport property model were tested on mobility and Seebeck coefficient respectively. This page shows testing set for the carrier mobility, including both N-type and P-type materials. The temperature and the carrier concentration corresponds to the experimental condition. The calculation will run at the same condition. Then the results were compared with experiment to see how agreement it is. This 2 page shows the results of mobility test. Generally, it can be said that the calculation agree reasonably with the experiment across all materials, carrying several order of magnitude. From, for example, at 300, the lowest, which is 3 for P-type copper aluminum oxygen, to the highest, which is N-type gallium arsenic. Most of the compounds show a bit light difference at a lower temperature. The difference becomes smaller at in high temperature range. This table shows compounds for testing stable coefficient model, and this page shows the result. Again, reasonable agreement with experiment value achieved for all these testing samples. And this table shows the testing site for the light thermal conductivity. In this site, I try to include as many elements as possible. Also, the kappa value of the testing material should cover a large range. Well, this table shows compounds and experimental and calculated kappa value at 300 Kelvin. I used two indexes to evaluate the model. So the Pearson correlation coefficient, which is a mirror of linear correlation between two variables, is 0.9999, which indicating very strong correlation between the calculation and the experiment values. Another index I use is the root mean square relative deviation, which is a mirror of the quantitative difference between two variables. The root mean square relative deviation here is around 30%, which means averagely the calculated value, kappa value, is 30% different with respect to the calculated values. I think this accuracy is relatively high. So after I have robust and relatively accurate program for calculating the transport properties, the next step is using it to screen thermoelectric material. I extracted all structures from the materials projected base. The selective standard as follows: sulfur, selenium, and tellurium as the only anionic sublattice. The band gap should be less than 1.2 electrovoltage because good thermoelectric materials are usually narrow gap semiconductors. The energy above convex Hall should be less than 0.1 electrovoltage, so the obtained structure stable or highly possible to be stable in experiment. Also, symmetry are considered. For now, we only include the cubic, tetragonal, and isotopic structures into the calculation. Based on the above selected rules, I have screened around 463 structures, and there were 361 structures finished the whole process of the electronic transport property calculation. These two pictures summarize the results. Left for N-type, right for P-type. The y-axis represents the maximum Hall factor a compound can reach in the temperature range from 300 Kelvin to 1000 Kelvin. The x-axis represents the carrier concentration corresponds to this maximum Hall factor value. The red line means Hall factor value equals to 10 microwatt per centimeter per Kelvin square. Above this line, compounds are thought as promising and go forward to calculate their light thermal conductivity and figure merit. Some representative compounds are also marked in the picture. Among these compounds, 6 of them, including germanium telluride, tin selenide, lead telluride, lead sulfur, or tin selenide, are already well-known thermoelectric materials and have high Hall factor according to our calculation, which validates our method. This page shows some statistic data of 361 compounds and 94 promising ones to give you an overall impression about what they are. The materials are grouped according to their composition, number of atoms in primitive cell, and the crystal system. The statistic data shows that compounds with high power factor tend to adopt simple structure. For example, most of the promising candidates are binary or ternary compounds with number of atoms in primitive cell less than 20. Moreover, half of the promising candidates have cubic symmetry, 47 cubic versus 47 tetragonal and orthopic structure. Although the proportion of the cubic compounds among all compounds is much smaller. It would be convenient if there are some simple descriptors which can help quickly evaluate the thermoelectric performance of a material. Such descriptors should be easily calculated, such as the average atomic mass or the atomic volume. This descriptor can be combined with machine learning model to predict more complex properties. So the question is, for thermoelectric material, which kind of simple descriptor are related with the power factor or figure-meter values, or at least can be used to group the data? I found that in many formulas for the transport properties, this density of state effective mass MD or conductivity effective mass MC enters into almost every formulas related with electronic transport property. For example, current mobility is usually inversely proportional to MC, and carrier concentration and supercoefficient are proportional to MD. So these two parameters are highly related with the final power factor and figure-meter values. Let's see the results. In these two pictures, I plot the maximum power factor with the relationship of MD divided MC. The increasing trend is clear. I also calculated the Pearson correlation coefficient between these two variables. For N-type is 0.4, for P-type is 0.58. The Pearson correlation coefficient is not very high, but still verify there is a linear correlation between these two variables. By adding one more parameter, kappa L at 300 Kelvin at the denominator. These two pictures shows the maximum figure-meter plot against this new variable. Again, there is a clear trend that the higher this variable, the higher the maximum figure-meter. The Pearson correlation coefficient for N-type is 0.89, while that is 0.62 for P-type. Although such a correlation coefficient is still a bit low, we believe using these three parameters, or the index most relevant with them as input in a machine learning model, could result in a high accuracy prediction of the figure-meter. This is actually the next step we want to do. Okay, so next I will introduce some promising compound we found during the screen work. The first group of compound I want to introduce is this copper, arsenic, sulfur like compounds. There are 15 such compounds, and these compounds have the same crystal structure with space group P213, and they belong to parallel type structure. We found that they are very good P-type thermoelectric materials. And this page shows their band structure. I use these 4 compounds as an example. Their CBM can locate along several different paths, but their VBM just along the gamma M path. The band degeneracy of the point along gamma M path is large, n equals to 12, which means there are 12 symmetry equivalent carrier pockets in the breeding zone, which will result in a very high density of state effective mass. Meanwhile, the VBM are dispersive and should have small conductivity effective mass. According to our calculation, they truly have small MC and large MD. As discussed in the previous slides, these compounds are expected to have a high Hall factor, and their Hall factor are extremely high in a wide range of temperatures and carrier concentrations. The maximum Hall factors of some of them, such as copper, arsenic, selenide, copper phosphorus sulfide, and rhodium arsenic selenide, can even be higher than 100 microwatt per centimeter per Kelvin square. Just a reminder that the power factor of those state-of-the-art thermoelectric materials, such as bismuth pyrite, laterite, they are usually 30 to 50 microwatt per centimeter per Kelvin square. So, however, we also found that this group of material have high less thermal conductivity, as this picture shows. And due to that, the maximum figure merit of those compounds are not much higher than those state-of-the-art thermoelectric materials. So for this group of compounds, the most important way to improve their figure merit value is reducing their less thermal conductivity, which can be achieved, for example, by alloying among these compounds. Cadmium selenide 2 is one of the good N-type thermoelectric materials we found. It's also a cubic structure with space group Pa-3. It also belongs to the pyrite type structures. This is its band structure. The VBM is at the gamma point, while CBM is along the gamma R path. The CBM is dispersive and have small conductivity effective mass. Meanwhile, the band degeneracy of CBM is large, equals to 8. So it also has a large MD divided MC value. And this page shows its transport properties. Its power factor is relatively high. What's more important is it has quite low less thermal conductivity. So its figure merit could be higher than 1 in the high temperature range. So the above introduced cubic compounds. Next, I will introduce some orthohombic structures. The most interesting one is this tin selenide-like compound. Tin selenide single crystal is a well-known thermoelectric material with record high figure merit 2.6 at 900 Kelvin. Its solid solution and polycrystal also reported to have high figure merit values. So it's natural to think for those compounds composed by the element near tin and selenide in the periodic table and adopt the similar crystal structure should also have the good thermoelectric performance. Luckily, the structures extracted from the materials project include such compounds. The tin selenide has 2 phases, a low temperature alpha phase with space group PNMA and high temperature beta phase space group CMCM. Compound similar with alpha phase include 5 ones. The unit cell contain 8 atoms and adopt this double layer structure. In each layer, atoms are connected in a distorted zigzag form. The adjacent layer along the z-axis are connected by a combination of van der Waals force and electrostatic attraction. And this page shows their band structures. They are indirect gap semiconductor. And there are multiple band values near the gap for both conduction band and valence band. Meanwhile, these band values are highly anisotropic. Since these compounds belongs to cubic, orthohombic crystal system, the band degeneracy of these band values are not very high, usually equals to 2. According to our calculation, this group of compounds are best to be N-type than P-type thermoelectric materials. Their N-type power factor could be higher than 10 microwatt per centimeter per Kelvin square. The exception is germanium telluride. Both its N-type and P-type power factor can be higher than 10. You see, compared with the power factor of those cubic compounds I introduced above, such a power factor value are not so high enough. However, I found this group of materials have extremely low lead thermal conductivity. Besides germanium telluride, the lead thermal conductivity of this compound at 300 Kelvin are already lower than 0.5 watt per meter per Kelvin, close to the amorphous limit. So we also calculated the phonon velocity and the analysis its phonon velocity and the Grayson parameter. So such a low lead thermal conductivity is mainly comes from its large Grayson parameter, which indicating the strong unharmonicity intrinsically in the lattice. And due to such a low lead thermal conductivity, their figure of merit value can be higher than 1 in a wide range of temperature and current concentrations. And compounds similar with beta phase tin cyanide include 2 compounds, lead cyanide and lead sulfide. The unit cell also contain 8 atoms and adopt this double layer structure. In each layer, atoms are connected in a less distorted way. And this is their band structure. Same as that for tin cyanide, they are direct gap semiconductor with band extremer along the TY path. There are also multiple band values near the gap for both conduction band and valence band. And for these 2 compounds, both its N-type and the P-type thermal power factor are high. Their lead thermal conductivity, although not as low as those alpha phase, but still very low, mainly due to their low phonon velocity and large Grayson parameter. And here shows these 2 compounds figure of merit. So both compounds are excellent N-type and P-type thermoelectric materials. The reading. So if you are interested in the in our works, you can get more detailed information from these 3 papers. The first 2 is a theoretical introduction about the AICON, and the third one is apply AICON to screen and find some promising thermoelectric materials. So this is the end of my second lecture.
Yes, it's the next lection. Maybe someone have a question about icon. Так. Type a question. Question. No. Wait.
May I ask a question?
Yes.
Yes. So my question is, in real crystals, there are a lot of different defects. For example, threading dislocations.
Yeah.
And in real crystals, the mobility of the electrons is, in certain cases, for example, when density of dislocation is higher than 10 powered by 7, dislocations play a crucial role in mobility. So they determine the mobility. Is it possible somehow to use ICON to take into account dislocation in some ways?
Oh, this is a good question. Yes, actually, I always want to do this these things. Let me. So first, for dislocation influence of the lattice conductivity, yeah. Of course, you can end the contribution of dislocation from to it, but for now, I didn't find easy model to evaluate the influence of defect dislocation, especially if you want to consider the dislocation. The main place is to calculate the relaxing time from dislocations and ended them together. So there is, for now, I didn't find a good model to to describe how to calculate the relaxing time from the dislocations. So, but I have some. I have read some papers. It has some complex models, but so we are still studying these things. And as for its influence on electronic transport properties, it's still the problem about how to calculate the electronic relaxation time from the dislocations. I think it's still quite a complex work. But consider the utilization of icon is the first screen. I mean, the first and the fast screen of of a large amount of materials. So I think at this stage, the influence of dislocation can be neglected, and we can focus on the main contribution from the phonons and ionized impurities to. And in the following study, when we have some candidate compounds, we can do more study, such as influence from the dislocation, grid boundary, etc., etc. Yeah.
Okay, thank you.
Okay, maybe more question? Someone typing question. Yeah, Tao, question in chat.
What's the reason for? Okay. Yes. Yeah. Okay. So you're asking about the large difference between the calculation and experiment value in a series of potassium compounds. Okay. So, well, I think the largest difference is mainly, yes, for this potassium chloride, yeah, it's the difference is a bit large. Yeah, actually, I have checked this this calculation. Let's say, no, my model. We use phonon velocity and Grayson parameter to indicate the that's how to say, to indicate the harmonicity in the lattice. So actually I found the calculated lattice conductivity are very sensitive to the Grayson parameter we calculated. So even, for example, we know this this compound is a very stable compound. I mean, it's experimental mirrored lattice conductivity. No, experiment mirrored Grayson parameter, perhaps just 1 point, etc., etc. But I found my calculated Grayson parameter is a bit large. Yeah, maybe large 0.5 or 0.7. So which, I mean, even such a low difference will make the final, final results quite different quite a lot. So I think the difference is mainly because so our Grayson parameter, calculated Grayson parameter, is not very accurate. It's overestimated. So the calculated kappa are underestimated. Yeah. Any more questions?
Tatiana type a question.
Thank you.
Okay, if not more question, maybe we now stop and continue in 6 p.m. next link and next lecture, because we have a schedule.
Okay.
Окей, ребята, все, ждем вас в 6 часов по следующей ссылке по расписанию. Всем спасибо.
Спасибо.
Илья.